Dim. Stellar evolution. Stellar meaning stars and evolution meaning change. So this is how stars change. We often compare it to a life cycle of a human. So we might say it's a baby, we might say it's an adult, we might say it's an old age. So first, no matter the size of the size is going to determine what path a star is going to take. But regardless of the size, all stars go through the first three phases. Can anybody remember the name of a cloud of gas and dust? That would be a nebula. A nebula is a big cloud of gas and dust. When that nebula starts to contract, it's going to start to spin. Temperature is going to increase. It may burn and produce light, but that's only because of gravity, not because of fusion. When this happens, we have a protostar. After a protostar, when our gases become stable, by stable I mean gravity pushing in is going to equal the fusion force pushing out. Imagine hundreds of atomic bombs going off and exploding at the same time. That's going to produce a big outward force or pressure, but gravity pushing in is going to equal that pressure, so it's stable. During this phase, the star is going to start to fuse hydrogen, taking hydrogen, forcing it together to form helium. This is called a main sequence star. So all stars go through these three stages. Now, depending on their size, their path is going to look a little different. So for a one solar mass, that one solar mass is the mass of the sun. So 10 solar masses would be 10 times greater. 0.5 solar mass would be half the size of our sun, so on and so forth. So a star, much like our sun, is going to, when it runs out of hydrogen, is going to start to burn helium. So it's going to take two helium atoms and fuse them together. The core is going to become unstable, and the outer shell is going to expand. So it's going to get larger because it's expanding, and it's going to turn red because it is cooling down. We call this a red giant. When our red giant runs out of helium, our core is going to collapse and our outer layers are going to expel in what we call a planetary nebula. Our core is going to remain after a planetary nebula, and it's going to continue to burn, and we're going to call that a white dwarf. Once it runs out of energy, the light's essentially going to go out, and we call that a black dwarf. Now, for a star 10 times more massive than our sun, it's going to go through a nebula, protostar, main sequence. After that, the step's going to be similar. Instead of burning hydrogen, we're going to burn helium, just like our red giant. It's going to become unstable. The outer shell is going to expand, so it's going to become larger, and it's also going to cool. So it sounds a lot like the red giant phase, but it's larger. So we're going to call that a supergiant. After a supergiant, so after it's done burning a helium, it's going to have enough gravity that's going to start to fuse some other things. So our core temperature is going to increase as carbon atoms are formed from the fusion of helium. Gravity is going to pull the carbon atoms together, and additional fusion is going to occur. We're going to form oxygen, nitrogen, and iron. Iron is the key element. Once it starts burning iron, it's going to become very unstable. The core temperatures are going to rise over 100 billion degrees. As the iron atoms are crushed, the repulsion force, kind of like atoms, when magnets, when you put two opposite ends of magnets together, they're going to try to pull apart. So the repulsion force is going to overcome gravity, and it's going to explode outward in a shock wave. We call this shock wave a supernova. And scientists have been able to directly observe a supernova, which is pretty cool. After your supernova, you're going to have the core remain, and that's going to be called a neutron star. Now moving on to very massive stars, 25 times more massive than our own sun. So these are huge. Again, it's going to go through the first three phases: nebula, protostar, main sequence. Afterwards, you're going to see that the hydrogen, instead of hydrogen, is going to burn helium. And you're going to see these two boxes are the same because we're also going to have a supergiant. These supergiants will be larger than the other supergiants, but we still call them supergiants. You'll see this box is the same because they're also going to go through a supernova. The difference comes in afterwards. With a supernova of a very massive star, the gravity overcomes the nuclear force, and it keeps protons and neutrons from combining, and the core is going to be swallowed by its own gravity. We call this a black hole. Now, it's not really a hole. It's not like you can go in one side and out the other, at least not to our knowledge. It's not like a hole that you would dig in your backyard. It's essentially a sphere. So it's a sphere that is just so dense that it's going to attract anything that gets too close to it. And light itself, light has a particle called a photon. That particle, a photon, has mass. Since it has mass, if it gets too close to our black hole, it's going to get pulled into the black hole. And that's why we can't see them, because light can't escape. We can't shine a flashlight on it and have the light bounce back. So we can see evidence of black holes, but we can't actually see the black hole in itself. Next up, I'm going to show you a video of some scale models so you can see like a size comparison between a main sequence star, red giant, supergiant, and things like that.